So how's the class? How about the network class? Too easy? No feedback? Too early in the morning? What do you guys think?
It's
Any
okay
comment you guys
so
want to
far.
improve?
It's okay so far.
Okay, so far, so meaning it's too easy, make it more challengeable?
No, not easy.
Okay. Any comment? All right, so today we're gonna talk about the new thing, and we call the error detection and correction. So give me a second. Hello. Hello. Okay. Hello. So internet connection is unstable. Which computer? This computer. So you know what is this? The Zoom is very stable afternoon, but very unstable in the morning. So I'm doing a CSE310 and 310, exact the same setting, but in the morning is some, I don't know why, but much slower and more lags. Okay, try again. Hello. Oh wow. Okay. What can I do? So I'll try to speak slow. So today we're going to talk about bit error in a link. So what's going to happen if your data is somehow corrupted, somehow compromised? Something like I intend to send 1010, but if somehow something happened, then 0 become 1, something like this. We call this isolated error, 1-bit error. Okay, or if I meant to send 1110, then something happened, then every bits are converted to 1. Then we call this a burst error. Okay, so it could be happen by any method, something like the spike signal. It has happened because it is an analog domain. Say the signal look like this, and someone turn it off the microwave in the middle, then there is spike signal. Therefore, the sections related to this point is corrupted and compromised. Something like every bit look like 1 instead of 1010 information. So we call this a bit error. And if 1 bit has happened, we call isolated errors, bit errors that do not affect other bits. The burst error, a cluster of bits in which several errors occur, something like we discussed in here. Okay, and burst error increase the data rate, of course. Why? Because 1 microsecond of impulse noise will affect 2 bits when data is 1 Mbps. Okay, so my size is 1 Mbps, and every bit positioned at 1 microsecond, right? Because I'm sending 1 Mbps and every bit positioned at 1 microsecond. If there's something bad happen in that duration, meaning at most, if I have 1 microsecond duration error, duration impulse from other sources, it at most impact my 2 bits. Clear? if I have 100 Mbps, then 1 bit positioned is 1/100 microsecond. Clear? Therefore, if it happens for 1 microsecond, meaning the bits impacted at most 101 bits. Clear? Okay, very simple geometry, right? So the first error is a poor and the bad thing. And if it happens, there is no way to recover. But if there is a 1-bit error, if I know there is 1-bit error, I may recover this. Okay, then how? This is what we're going to talk about today. So dealing with the error, so receiver must be aware that error occurred in a frame. Therefore, I may ask, oh, please send me again, or hey, wait, I think I can correct it. Some kind of method I'm going to teach today. And the very basic thing is receiver need to know for the first time, right?
Yes, sir.
Yeah.
What is fading effect?
Oh, right. So fading effect. So it could be happen by impulse attack. Fading effect is like this. So I am the receiver. And my signal, let's say it is my base station. Base station like your cell tower, your LT station. The signal comes from here to your phone directly. Then we call this LOS, line of sight signal communication. Okay. But what if there is a building in front of me, a building behind me? Then what happened to the signal? So wait for a while for the slide is coming up. Okay, then my signal is not coming directly to me. At the same time, the signal propagates this way and comes in, reflecting, and comes back. Reflecting, comes back. Therefore, I am receiving not just LOS, but at the same time, I'm receiving multiple signals at the same time. Therefore, I intend to do this information 10101000. Come up. Then, because of this fading information, signals are shifted and receiving again. Therefore, it impacts the receiving.
So you're saying that when the signal is bounced off, it shifts?
Okay, I'll try to explain one more time. So let's say So let's say I want to communicate with the others. When there is a nothing there, and I can have a direct communication, meaning the signal is very clear. But if I have some tackles, some obstacles that hinders my communication, the signal that I'm receiving is not from one source, but multiple paths. So one path, the original path is line of sight, and these called NLOS, non-line of sight. The signals are reflected. The same signals are reflected. Therefore, travel time of this signal is different. It's shifted. Therefore, I'm receiving signal, but at the same time, I have much more power than I expected because of multipaths. Then we call this pattern as a fading effect. A signal is faded, shifted somehow. It impacts the original communication. Therefore, my information intended 1010 is somehow compromised to the 01011011 pattern, right? If let's say I'm talking to like David across the room, then I can say something. Then my voice is echo. But if we're receiving, at the first time, he may receive it correctly if there is no obstacles. But if I have many obstacles, then signals are bouncing back, but he will see the some echoes. Some echoes shifted is far away, that is fine. But echo shift is very small, then he may not receive perfectly. Therefore, it impacts the signal reception. That is the fading effect. Therefore, it usually impacts the burst error. Okay, so fading effect affects the burst error, or the impulse noise, the short, strong signal, something like someone turned on the microwave in the middle of your communication, that will impact your communication. Clear?
Clear, thank you.
Okay, so how we deal with the errors? Okay, I think someone just keep trying to admit it, but struggle on it. Okay, 1 second. Let me switch the network. Do the based on my iPad. So dealing with the errors, how can we? So we have to first know there is an error. And how do you make sure it is error or no? How do you make sure your communication is intact? So we are adding some additional information. We call the adding redundancy. Then we make sure the information is correct or no. Okay. So for the first time, receiver must aware that error occurred in frame. So need to have error detection mechanism, meaning the simpler. Error correction mechanism is more complex than error detection. Error is, oh, there was error, I don't know. But if there is an error, oh, I think I know which bit is error, then I can correct it. Therefore, I need more information for the error correction, okay? So the main goal of the communication is your receiver must receive the correct frames at all times. Therefore, the communication is succeeded. If not, I have to send it again, or I have to find an alternative way to retrieve the correct frame, okay? So there is two possible strategies. First one, add information redundancy to correct error. So this is called the error correcting code. Or I can ask the sender, please send me again. These, I have no ability to correct it. Send me again, okay? But at this time, I only have, the second thing, I only have ability of detected. So in practice, both are employed. Okay, we're gonna talk about it from the very simple thing. So error detection and the parity bit. Single parity bit check. So what's the parity bit check? Okay, adding single parity bit at the end of frame, parity 1 if 1 is odd, and 0 otherwise. What does this mean? So let's say this is my information. 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Say this is my information. Parity bit does count the 1. How many 1 do I have? I have 1, 2, 3, 4, 5, 6. Oh, therefore my parity should be 0. What if it is 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0? What if this is my original messages? Then I'm counting 1, which is 1, 2, 3, 4, 5. Then I'm adding 1. Clear? So I'm adding parity, either 0 or 1, by counting 1. Okay, let's see how it does work. So single parity check can detect any odd number of errors. Let's say I received the information, some pattern. Okay, in the end, after receiving this information, 0, 1, 1, 0, 1, 0, 0, 1, 1, then I can check if this is correct or no. The receiver must aware this is correct frame or no, right? Therefore, what do I do in this scheme? I do count 1. So I count 1, 1, 1, 1. Oh, this is 5, meaning something bad happened. this is not correct information. This is not correct frame. Then what can I do? I can ask, send me again. I have no ability to correct it, but I have ability to detect it. Okay, something like this. Let's say this is receipt 0110101, but original message was different. Let's say something like this was the 0001101. Let's say this is my original. This is what I received. My receipt is error. My original 1111, right? My original is not converted properly, but I have no ability because count of 1 is even, meaning parity bit check is very simple. It only has ability when the odd error happen. Okay, when the error happen evenly, in this case, 1, 2, 3, 4 errors happen. Right? In this case, I have no ability, but I have ability to half of the 50% of error is detectable by having a parity bit. Clear? Okay, and it has no ability to tell you where the error took place and how many error occurred. I only able to say error or no at 50%. Okay, so it also not useful for the burst error, but your link is very reliable. If it happens that there's only 1 bit error, then you can use this mechanism. Okay, so one more step. I have 2-dimensional parity. So I know what it is. So these blue cells are parity bits. And this is my information. What do? I make into the 2-dimensional error. So I sequentially send from this first row, then second row, and third row, and fourth and fifth. What do? I'm adding parity on 2 dimension. It's the same thing what I did in the previously. So I count 1, 1, 2, 3. Therefore, I have to add 1 in the first row. Second row, I count 1, 1, 1, 1. Oh, this is even number. I'm counting. I'm adding 0. I make the ones 1. So you are repeating until this point. 1, 1, 1. Therefore, you have to add 1, right? Then you are repeating this on a column. So you count 1, 1, 1. Oh, I have to add 1 in the first column. Then repeating 1, 1. Oh, even number 0. Okay. Then you do 0, 0, 1, 1, 1. Oh, I'm adding 1 in the 7th column. Then in this case, I'm adding 1, the last one, 8th column, 1, 1. Oh, I have to add 0. Okay. That's it. This is 2-dimensional parity. What's the advantage of it? So it can detect that it is more advanced version from the previous because I can detect 1-bit error, 2-bit error, 3-bit errors. Let's practice. Let's say this is 0, converted 0, and converted 1 and converted 0. The first column, first row, 4th, 5th, 6th one is error. Let's say 3 bits are error. Okay. Let's start from the simpler one. So let's start from, let's start from this bit is error. What can I do? Okay, this bit error converted to 0, right? Error happened to 1 to 0. Then what can I do? I'm checking number of 1 in a row, 1, 2, oh, 1. Oh, I think this one is error. Then you keep repeating the second row, third row, fifth row. Then there is no error, right? There is no error. Then you are repeating on the column. First column, no problem. Second, third, fourth one, you count 1, 1. Oh, it should be 0. Then it is problem. Okay, then no problem, no problem, no problem. Then no problem. Meaning I can isolate which column and which row creates error. Ah, this bit is error, meaning I have ability to correct it. Clear? Okay, let's make a more advanced one. Say I have the bits are converted to bits error in the 2 bits, this guy and this guy. Meaning the first row, 4th column and 5th column converted to 1 to 0, 0 to 1. Okay. So 2-bit happen, 2-bit errors. So column, row first, 1, 1, 1, 1. Oh, correct. Everybody is correct. Okay. The row then, the column then, okay. The first row, okay. First column, okay. Second column, okay. Third column, okay. 4th column, oh, error. 5th column, oh, error. 6, 7, 8, no problem. I have ability that I don't know which row is happened, but I know this column has error. Therefore, I can detect error happened in a 2-bit error. Okay, at this time, I have no ability to correct it because I don't know. I can only know this column is error, but which row is an error in this case, because I have no clue in the row detection. The same thing happened to the 3-bit. Let's say one, 0, 1. Then I'm count 1, 1, 1, 1. Oh, error. And no problem. Then from here, okay, error, error, error. Error, error. Then I can say, okay, I see this one is error. This column is row. I'm not sure, but this row is error. But it's not clear because I don't know how many bits are error. So in this case, I can guess 3 bits are error, but it's not precise. There's many cases like this. So in the best case, I can detect up to 4 bits, something like error, 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 error. Then for 1, 0, 1, 0. Then I can detect this guy, this guy, this guy, this guy, and this guy, this guy, this guy, and this guy. Okay, 4-bit errors. Then I can detect, oh, something wrong. From the 5-bit, it is very hard to maintain it. Okay, 4-bit at most in the best cases. It usually can detect up to 3 bits error, and it can also correct in 1-bit error when I know it is 1-bit error. Okay. Okay, it is more advanced one. What do I sacrifice to get more advanced one? I'm adding more redundancy. Previously, I only add 1 bit in the parity bit in a 1-dimensional parity. Okay. In 2-dimensional, how many bits do we add? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Out of total, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 7 by 5, 35 over 13 bits error under that redundancy. Do you see? So information I try to deliver is 35. So to make sure this information is correct and to have ability 1-bit error, I'm adding 13 bits. Therefore, my message is 48 bits. Okay, so somehow overhead is too big. I cannot handle this. Okay, but conceptually, this is good example. Okay, let me go to the next place. So CRC recovers almost everything. So CRC is commonly used in, we are still using CRC. And most of the wireless network comes with the CRC, okay? So what's the CRC? CRC is a cyclic redundancy check. So add K redundant bits on a bit messages. So my design should be, K is small. Your redundancy should be much smaller, and you have to make the minimum of it to deliver N messages, okay? So you have, design goal is make K very small compared to the N, therefore overhead is very low. So for example, CRC in practice, 32-bit CRC is adequate for 12,000 bits, okay? It's very efficient. How does it work? So example, this one maps to this CRC code. Okay, I'm gonna tell you how does it convert it. So this is 2 power of 0, 2 power of 1, 2 power of 2, 3, 4, 5, 6, 7. Right? Therefore, then I can say, oh, 2 to the power of 7 plus x6, no. x5, no. x4, yes. x3, yes. x2, no. x1, yes. And 0, no. Okay, so we usually don't make this one, the last one, as a 1. Okay, if it happens, then we are using x7 plus x4 plus x3 plus x1 plus 1, something like this. Okay, but we just understand, you just understand that, oh, how does 7 happen? How does 4 happen? 3 happen, 1 happen, okay? So we are converting this maps, this code to this number, okay? So the bits of message to be transmitted become the coefficient of the polynomial. So the one word we have to remember is n-degree polynomial, meaning represent n plus 1 bits message as n-degree polynomial. Ah, this is what I just did. The binary, the bits to the binary representation. Ah, that binary representation can be converted to degree polynomial. Clear? Maybe too simple. If you have a question, please raise your voice if any point is not clear to you. Can I move on? Okay, now we just understand the code key and let's see how it works. So let me show you how does it work. So your code is, CX x3 plus x2 plus 1, meaning 1, 0, 1, 1. Clear? I can make 1, 1, 0, 1. From the back, I start to count it, and it turns out 1, 1, 0, 1. Okay, so this is my code messages. And this is actual messages. What do? My message is here, and I'm adding redundancy, code length minus 1 as a 0. There's a reason to do this. I'm going to explain to you. Then I'm divide my code to my messages. Then division is XOR in a bit. So 1, then 1, 1, 0, 1. Since it is XOR, 0, 1 is 1, 0, 0, 0, 1, 1, 0. 1 is here. Then you keep repeating until you get 1, 0, 1, which is my remainder. Okay, then you are XOR with this remainder and message plus redundancy. Then the message is, the actual transmitted message is 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1. Okay, Now receiver received this information. Then if it is correct information, what happened? 1 0 0 1 1 0 1 0 1 0 1. Then your code is shared between sender and the receiver. Then what you do the exact same thing. Divide by code word. Then 1 1 1 0 1 4 1 0 0 1. Then 1 1 1 0 1. Then 1 0 0 1. Repeating 1 1 1 0 1. Oh, first one, second one should be 0 1. Therefore 1 1 0 1. Yeah, where am I? 0. Then there's 1. Let me try to do it again. So choose. So now given my message is 1. Hello? My connection is unstable. Okay. Whatever. Hello?
Hello.
Okay, thank you. So my network goes down respectively. Okay, so I'm sharing screen. I don't think has a started screen. Double click to enter. Okay, let me restart it. Come back. Do you see my slide? No, not at this time.
Not yet.
Nope.
No, okay. So this is my problem. Okay, let's have a 1 minute break. Then I'm trying to fix my this network issue. Let's have 2 minute break. Let me remake the room. Okay, disconnected this guy. Back. I'm sharing the screen. I'm sharing my desktop. Disconnected. June, I'm sharing. Can you hear my voice?
Yes.
Hear you.
Okay, all right. Thank you. So still lagging. I don't know why does this keep happening.
Professor, are you doing the recording with the iPad also?
No, I'm only recording on the desktop. So it is never happening on the other class, but in the morning it happened. I'm sharing the screen. Let me click it. No. Zoom issue. Is it Zoom issue? Stop it. Okay, starting.
Is it the iPad that's disconnecting or your computer?
No, iPad is there. Start sharing screen, but it doesn't show any contents on it. It has started sharing screen, right? Do you see my screen? No. I don't think so. So let me pause the Zoom recording. Okay. All right, come back to the point. I think the lagging is gone. Let me try it. Hello. Wow. Hello. Okay. Is it much better, right? My voice and the screen is synchronized much faster. Okay.
Yes, sir.
All right.
Was it network?
So I try to remember this. Okay. So I want to practice one, which is, let's say my message is 100111010, and my code is +1. Then let's solve this. How does it happen? So this is my message, and this is my code. What do? I convert it to the bits 1, 1, 0, 1. You know how I convert it, right? Okay. Then 1, 1, 0, 1 divided by 1, 0, 0, 1, 1, 0, 1, 0. I'm adding redundancy 0, 0, 0. With the length of code length -1. Then I divide it by my code 1, 1, 0, 1. Subtract is XOR 1, 0, 0, 1. And I do 1, 1, 0, 1. Then 1, 0, 0, 0. And again 1, 1, 1, 0, 1. 1, 0, 1. 1. 1 again. 1, 1, 0, 1. 1, 1, 0, 0. 1 again. 1, 1, 0, 1, which is 1, 0, 0, 0. Then 0, 0, 1. 1, 1, 0, 1. 1, 0, 1. This is my remainder. Okay, so my messages plus the redundancy. Then what I do is remainder XOR to this my message. Therefore, my actual transmitted message is 1, 0, 0, 1, 1, 0, 1, 0. Therefore, XOR to this is 1, 0, 1. This is my messages. Okay. Let's say this messaging is transmitted. Message is 1, 0, 0, 1, 1. 1, 0, 1, 0, 1, 0, 1, 0, 1, right? 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, this is what I transmitted. So what I transmitted is 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is what I transmitted. 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0. Okay. Then my code word is shared between sender and receiver that I repeating 1, 1, 0, 1. Then I'm keep dividing this one time. If the message is correct, remainder will be 0. Why? Because what I transmitted plus remainder, and the code is here. Let me practice on it. 1, 1, 0, 1. 1, 0, 0, 1. One time. 1, 1, 0, 1. Then 1, 0, 0, 0. Then again 1, 1, 1, 0, 1. 1, 0, 1, 1. 1, 1, 0, 1. Then 1, 1, 0, 0. One more time. 1, 1, 0, 1. Then 1, 1, 0, 1. Then 0, 0, 1. 1, 1, 0, 1. Remainder is 0. Guarantees my message is correctly delivered. If any of bits what to transmit is converted to and corrupted, then it will never going to make remainder 0. Okay, this is fundamental example. Fundamentally detect what is error, is the error happened or not. Okay, so let's do one practice. So let's practice your message is message is 1101 0 1 1 1 1 1 1 1 0 1 0 1 1 0 1 0 1 2 3 4 5, and your code messaging 1 1 0 1 0 1 2 3 4 5. Your code 1 0 0 1 1. Okay. So what is your transmitted messages? And what, so can you repeat? So let me, wait. So 10011 is my code. My messages is 1101 011111 50. Okay, let's practice. So show your steps and what is transmitted messages, and second, verify at the receiver. Clear? Let's do this. You can practice on the note, and you can submit on the Google Classroom. Then I'm going to make a Google Classroom question now. Classroom. This 1-1 and so you know what you should do, right? You understand what we are doing, and I'm sure you know what we are doing. And submit your work after capturing it. And let's do this one as a quiz. Since we are doing online class, with this interactiveness really helping and checking your attendance too. Okay. All right. Let's have 3 minutes to practice it and submit your work on the Google Classroom after taking a picture of it. Okay. Let's do. Let's spend 5 minutes of it. Okay. Everybody understand, right?
Yes.
Okay, thank you. So you still need to upload your answer. Okay, that I'm not marking as good or no, but I'm using it as your attendance. Okay, so how do you start? So this is code. This is my messages. What do I do first? Based on my message, I'm adding redundancy as a length of your code -1. 5. So I'm adding 4 redundancy. Then 1001. Then I can do here 10011, which is 10011. Again 10011. Then 111. 10, which is 00001, 10011. My message is 11010. Then one more time, 10011. Then 1. It's gone. Okay, so you know how to do, right? You have to do adding. You have to add the redundancy, then dividing it. Then if there is a remainder, you are adding on at the end of your messages with the XOR. Then receiver receive that information. If the message is correct, you can divide with the code and remainder will be 0. If the remainder has some value, then meaning that your message is corrupted. Okay? So this is how you do the CRC. Let's quickly read through.
So what's the answer?
Okay, slideshow. So CRC, oh, now we understand what it is. Represent n+1 bit messages as an n-degree polynomial. This message to polynomial to this messages. Okay, the bits of message to be transmitted become the coefficient of the polynomial. Oh, coefficient of the polynomial. And polynomial, so any polynomial bx is divisible by the polynomial cx, and therefore your code word is much shorter than your messages, and your code is called divisor, and cx and bx are the same degree. The remainder obtained by subtracting cx from bx, and modulo 2 arithmetic subtraction is XOR operation between coefficient. We know what that means. Therefore, we can practice this. So example, bx of this guy, cx is this, the remainder is x2, meaning this bx is 1001, this cx is 1101. If I divide these two, meaning XOR, right? XOR with this, then 1 is 0, 0 1 is 1, 0 0 is 0, 1 1 is 0. So this is my remainder. Clear? I assume you know how to do the XOR. I assume you know how to do bit operation. They're very basic thing, okay? So CRC calculation, the process is multiply mx by x over k to obtain tx. K is a degree of the cx, and divide your message by your code word and subtracting remainder rx from the tx, then obtain px, which is XOR result with your messages plus, so your messaging XOR remainder, which is what is transmitted, and obtain px by dividing your messages and rx divisible by cx. If it is divisible, meaning your message is intact. If there is some remainder after receiving it, something wrong, okay? So example, we did this and selection of cx, and how do you select the cx properly? So bit error can be seen as a polynomial ex and added to the px. Error remains undetected if error is a dividable in cx. In some cases, very rare, but it hardly happen. So when you make a nice cx, nice code, that this does not happen in reality. In very old cases, it could happen, but in most cases it doesn't. So single bit error is coefficient non-zero. So all single bits are detectable. Double bit errors, CX has at least factor 3 terms, then it is able to detect a double bit. Odd number errors, CX contains a factor of x plus 1. It is available to detect it. Any first error or less than k bits, or most first errors are larger than k bits are detectable with the CRC. So this is industry's choice. We all using CX in the Wi-Fi, in the communication, in LTE, in the landline. So this is commonly used as CRC code. CRC32 is what we are using. So in the notebook, we cannot compute this because it's too long, right? But in computer, it is easy to do this, right? And CRC8 look like this, and we are sharing a CRC code between sender and the receiver to make sure your message is properly delivered. So fundamental of the codings, map a k bits word to the n bit word. Oh, we know what that means. We are adding redundancy for detecting the error, also to correct the errors. So weight of word, the number ones in the word, 1, 2, 3, 4, 5. We are using a weight of word as count of 1. And Hamming distance between x and y is XOR with the 2 value. So Hamming distance basically, how many bits do I need to convert it to make from x to y? Meaning XOR, x and y is XOR, okay? For this case, this is 6 because 1, 1, 1, 0, 0, 1, 1, 0. So how many bits do I convert it from x to y? How many bits are converted if the x want to be y? So this bit need to be converted, this bit need to be converted, converted, no, yes. So if I count it, 1, 2, 3, 4, 5, 6. So distance 6. Okay, so we call the Hamming distance of D is n to 6 and n to D, and this computation is happening here. Number of word distance up to this guy D. Okay, maybe mathematical, maybe confuse you, but the concept of it, how many bits do I need to convert it to x become y? In this case, easy to understand. Oh, 6 steps. That's called Hamming distance. And the simple mathematic is XOR between x and y. Okay, so minimum distance is minimum Hamming distance out of all distance in a code. We're gonna practice of it. So Hamming distance, Hamming code, the example. So if I want to do, so my main goal of this doing is detect the error and correct error. Hamming distance can correct error. Okay, if there is 1 bit error. Let's do an example. Let's say this is my messages, 100, 1101. Okay, so power of 2, which is 1, 2, 4, 8, 16, 32, 64, 128. You know what it is, right? Then you make empty spot every 2's power. Okay, then you fill in your messages on where is not 2's power. So 1, 0, 0, 1, 1, 0, 1, 0. Okay, then this position, I want to fill out this position. What do? I do count, discount, skip 1, 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 discount. And I count number 1. 1, 2, 3, 4. Then I should be a 0. The same mechanism that we use in the parity. Okay. Then 2 position. Count 2. Then 2 at this position. I have to fill it this one. What do? Count 2, skip 2, count 2, skip 2, count 2. How many 1 do I have? 1, 2, 3. So I should be 0. I should be 1. My goal is make 1's count to even number, right? Then I have to fill out this format. What do? 4 count, skip 4, 4 count. So if it is invisible, there is no data, it's counted as 0. So how many bits do I have? 1. So I have to make 1. Then it is even number. From 8, what do? 8 position, skip 8, and 8 position. So meaning 1, 2, then it should be 0. Clear? So I just fill out the empty blank spot, 0, 1, 1, 0. Then this is my messages. Okay? So let's say you just received these messages. Then what do? Then I know where's the code position. Code position meaning to the power. Then from here, I count this guy, skip this, count this, skip this, count this, skip this, count this, skip this, count this, skip this, count this. So I count the number 1, 1, 2, 3, 4. Oh, this is correct. Okay. From here, count 2, skip 2, count 2, skip 2, count 2. Okay, count number 1, 1, 1, 2, 3, 4. Oh, it's correct. So you keep repeating this. Okay. Whenever there is an error, I have ability to detect it. So let's say I made so this bit is D position 10 is compromised. Do I have ability to detect it and correct it? So if I pinpoint which bit is error, which means I have ability to correct it, okay? As long as I know there's 1 bit error. Let's correct this one. So I just received these messages, then I'm repeating what I just did. Then count this guy, every odd position, then count number 1. 1, 2, 3, 4. This is even number. Okay, 0 is fine. So this position is out of my radar, meaning they are all cleared out. Because I know there is 1 bit error and I want to know where is it? Where is it? Okay. Then from this point, what do? I count this guy, and this guy. 1, 2, 3, 4, 5. Oh, I think there's something wrong. So my candidate, my suspect is this guy, and this guy. 3 possible candidates, right? Because these position D3, position D7, position D11 is clarified before, right? By the P1. Now I'm checking P4. What do I do? P4, I count 4 of them, skip 4, and this guy. Okay, count 1, 1, 2. Okay, that is fine, meaning I can clear you out. Okay, then this position, what do I do? 8 position from here, count 1, 2, 3. Oh, this is wrong. So my suspect, you are picked twice. Okay, this is picked once. If there is error in a 1 bit position, oh, I can pinpoint. D10 position is error. This is Hamming code. This is Hamming code encoding mechanism. Okay, everybody understand what I did? Okay, so I have very nice do you see my notebook screen?
Yes.
Okay, thank you. So this video explains you step by step of the Hamming distance, exact thing what I did, but with the animation. Okay, so I'm gonna open this link. To everybody. So exactly the same thing that I did with the Hamming code. You can watch this. Okay, so I think you can watch by yourself by clicking it. Okay, so now we have ability to encode messages to detect error and decode message if there is no error, or I have ability, okay, there was a bit error, so I know, maybe I can correct it with the coding mechanism that we learned today. Okay, everybody clear is on today's class? Okay, so any question about today's class? Nobody? So I collected most of you, and 2 of you didn't submit it. Jaewon Lee and Yomnom. I don't know who's Yomnom, but Yomnom is missing. Okay, I don't think they are participating in the class. So I'm checking it. Who has the correct answer for the quiz 1? I think Yeun did correct answer. Good job. Oh.
Professor, are we gonna get a homework?
David did the correct answer. What was that?
Oh, are we gonna get a homework assignment based on this concept?
Yeah, the coding assignment. Yes. So I already make the Python notebook based on the Hamming distance and CRC. So you can practice the CRC and Hamming distance. The homework is very easy. I expect the first homework is easy, and then I'm increasing the difficulty in the following homework. Clear? Any question about the homework? So I will post the homework no later than midnight tonight, maybe early tomorrow.
Professor?
Yeah.
Do we have the midterm next Monday?
What's the schedule says? If the schedule said it is, give me a second. On the next Monday. Next Monday, right? Yeah, I think so.
317.
Any difficulty? David?
I think you're looking into the 373 algorithm class schedule.
No, I checked the 310 at the same time as court. The midterm 1 is still there, right?
Yeah, okay.
So
Professor?
Yeah, homework in and out, and something is there, but I'd love to have a midterm 1 on Monday. Should be fine, right?
So the midterm cover all the previous lectures?
What do you mean all the previous lectures? So what we learn in the class will be our midterm 1.
Okay, thank you.
So I want you to read the book, and I want you to read on the material that we cover. And I will upload the video. Yeah.
How do you take the midterm? Is by the Blackboard or?
Can you say that again, please?
How do you take the exam?
I will give you as a file, then you fill out the file and submit it, like a take-home exam. But it is on time. I will set the time on it. And you will be on the class, and you solve your question and take a picture of it or whatever method you are taking, and then you submit it.
Professor, do you have like 2 midterms on Monday? Do you have 2 midterms on Monday?
Do you?
Do we have like 2 midterms on Monday? Like C10 and
So
C10?
this is 310 class. 310 will be a midterm. And 373, if you're taking 2 courses, I think so, yes.
Can you make like on Wednesday one of them?
Huh?
Can you change the date to like Wednesday?
to Wednesday. Which
Yeah,
one?
7-3. Because I have
So,
other quizzes as well, and I kind of like really tough.
then delay this one, 310 to Wednesday. How about that?
Okay.
Update this class to the Wednesday. So 310 will be midterm on September 16th on Wednesday. So I'll post on it. I'll make a post. And I'll update this syllabus. Okay? All right, so just one note that the so Yomnom, I don't know who's a Yomnom, but he or she doesn't submit it. Just tell her or him. If no Yomnom, I don't know. It's hard to read it. Who's this guy? He didn't submit it. All right, thanks for coming today. And midterm is delayed to Wednesday. Okay, everybody happy? Okay,
Yes.
I will submit. I will upload the homework number 1, maybe today and maybe tomorrow if the too many things are happening. Okay. All right. Thank you, guys.
When will it be due by the first homework?
The 1 week
1 week?
or
Okay.
10 days, based on the difficulty. Okay. All right. Thank you.
Thank you.